Okay, so this is joint work with Alex Andoni, Daniel Su, and Share Sun. So in this talk, we'll be looking at the following problem that we call correspondence retrieval. So the learning problem is the following. Let's suppose you have k unknown vectors in d-dimensional space that you want to recover. But we have the following non-standard observation model. So you pick a measurement vector, and then you apply this measurement vector to each hidden vector and observe a linear measurement from that. But you observe this entire set of k measurements as one single unordered set. So what this means is that if I take all n of these sets, you wouldn't be able to set up a system of linear equations and solve because you don't know which entries correspond to the same underlying hidden vector. Right, so the difficulty in this problem is how do you find the elements in each set which correspond to the same hidden vector. And so the main challenge here is this parameter k. And so it turns out that this problem is already interesting just if you have k equals 2 hidden vectors. And this reduces to a previously well-studied problem called phase retrieval. So the standard setup for phase retrieval is the following. You have a single unknown vector, and again, you observe linear measurements of this vector, but you only observe the sign or the absolute value of this vector. All right, so in this setting, if this were a complex number, then you would observe the magnitude and you lose the phase information. And if this were a real number, you observe this up to a loss of plus or minus 1. And so this is a special case of our general correspondence retrieval problem under this identification. Another related problem is the mixture of linear regressions problem recently studied by Yi et al. And so the setup is the same. You have k hidden vectors, but you have the standard mixture model observation where you just sample one hidden component that you don't know and then observe a linear measurement with respect to that. So in this problem, Yi et al. Show that you can use tensor decomposition techniques to obtain a sample complexity of k to the 10d, which is the number of measurement vectors you need to draw. So one way you can think about this is you can apply this to our problem by treating the correspondence retrieval problem as a uniform mixture and obtain a sample complexity just like this. And so our main result is that in this variance of the mixture model, you can obtain optimal sample complexity. So under standard assumptions of what measurement vectors are drawn from, right, we only need d plus 1 measurement vectors to fully identify each of the hidden vectors. And the second contribution is that our solution introduces a fairly non-standard technique to solve this in the machine learning area. So we use the triple lattice basis reduction in order to identify the correspondences from an optimal number of samples. Okay, so this is our main result. So let me go into some of the technical details of how we arrive at this. So first, just to compare, right? So we go from k to 10 times d samples down to kd plus 1. And in the phase retrieval setting, the previous result is that you can choose 2d minus 1 measurement vectors a priori, and then this is sufficient to recover all possible hidden vectors x. Whereas our result is sort of an orthogonal result that says for any individual fixed x, if you sample d plus 1 measurement vectors, then with high probability that suffices. Okay, so the main algorithm for this goes to the following problem. So the subset sum problem. So we reduce this learning problem to a subset sum problem. So to remind you, the subset sum is the following. You have a target sum n, you have a bunch of numbers a1 through an, and you want to determine if there's a subset of the a's which adds to n. Okay, so subset sum is NP-hard, but it turns out to be an easy NP-hard problem in the following sense. So Lagarius et al. Showed that, in particular, if the A's are uniformly distributed within a bounded domain where the domain is sufficiently large, then you can solve this in polynomial time on the average case. So this uniform distribution is not essential, so we extend this to the case where you just need this summation to satisfy anti-concentration around any point. Okay, so how does this subset sum average case algorithm work? So this is where lattice tools come in. So a lattice is essentially an integer linear combination version of a vector space, right? A lattice is you first fix a basis of real vectors, and then you form all linear combinations of the basis elements, all integer linear combinations of the basis elements. And so, right, so you can write this the following way, where you take the basis and multiply it by an integer coefficient vector. Now, because we restrict the coefficients to integers, there's the following problem which makes sense in the lattice regime that does not otherwise make sense for vector space. And so this is called the shortest vector problem. So can you find a non-zero coefficient vector which minimizes the Euclidean norm of the product? So in other words, find the vector in the lattice that has the smallest norm. And the reason this is hard is that, right, so the basis elements of the lattice can be arbitrary. They could be exponential in norm, but sometimes, and as you'll see in our reduction, the shortest vector is going to be exponentially smaller than any of the norms of the basis vectors. Okay, so the shortest vector problem cannot be efficiently approximated within a constant factor unless NP is in RP. On the other hand, algorithmically, there's the following algorithm, which is called triple L lattice basis reduction. And this algorithm obtains only an exponential factor approximation to the shortest vector. So I say only exponential because this 2 to the d over 2 does not depend on the original norm of the basis elements that I give you. So in other words, the condition norm of the lattice does not show up in this approximation factor. So this is going to be, so the fact that this does not show up here is going to be key to how this algorithm is going to be able to solve the correspondence material problem. Okay, so now that I've introduced these tools, briefly the steps of the proof go as follows. So first we reduce this learning problem to the shortest vector problem with a certain explicit lattice basis. Now in order to apply a triple L to this, so first we need to identify what the actual shortest vector is, and what we are able to show is that the coefficients that produce the actual shortest vector contain the information needed to read off the correspondences, which then enable us to solve the linear system. Okay, so once you identify what the shortest vector is, you need to show that every other possible vector is too big to be returned by the triple L algorithm. So remember we have the exponential factor approximation. So we need to show that for every other possible lattice vector, it's exponentially larger than what we've identified to be the shortest vector. And so the way we prove this is by showing that for any fixed incorrect vector with high probability, it's large, and then apply a union bound argument over this. So then once we have steps 2 to 4, then this shows that triple L is sufficient to recover the correct coefficient vector. Okay, so we have 1 minute left. So briefly, just to recap, we define a new a learning problem with a new observation model, which is loosely inspired by mixture models and also generalizes phasor treatment. And we show that under this slightly different observation model, we can get much better sample complexity by solving sort of an algebraic problem that more explicitly utilizes good correspondence information. And we also introduce a technique, an algorithm based on a completely different technique in this area, a triple L basis reduction. All right, so thanks for listening.
Questions? Ohad.
So if the observations are noisy, can something be done, or is it hopeless?
So yeah, let me quote the previous speaker in saying all hell breaks loose in the presence of noise. Well, so what happens is, if you look at a subset sum problem, right? Suppose the A's have noise in them. How do you know if the sum of A's is m plus noise, or if there's something you're missing from the subset? So yeah, this technique does not apply to noise, unfortunately.
So you show that if you can solve the shortest vector problem, then you can read out the solution, but you have to, right?
Yeah, so
You have to show that if you can solve it approximately, you can also.
Yeah, well, so we show that by showing that every other vector within the approximation factor, well, so we show that there's no other vector within the approximation factor of triple L. So there's only one possible vector that can be returned by triple L, because it has this norm, and we show that every other vector has at least this norm. So that deals with the approximation factor.
Okay, let's thank Kevin again and the speakers of the session.